Okay, so last class we introduced something called the rate law. All right, now, oh, sorry, I'm muted. Let's try again. Okay, last class we introduced something which was called the rate law. The rate law. Okay, so the rate law is a little snippet of information that accompanies a specific reaction. The rate law is specific not just to every different kind of reaction. Every different kind of reaction has its own rate law, but it's also specific to the various conditions associated with that rate law. And what rate law does is it tells you how fast a reaction will proceed based on the concentrations of the reactants. Okay? So, again, hopefully this is a little bit of review for you guys. But let's continue that review and say, here's a chemical reaction. All right. I'm going to put some numbers in here just to make sure we are kind of thinking about the coefficients and their influence on the rate law. Okay. So here's a chemical reaction. And I would like to write the rate law for this chemical reaction. Now, we don't know the rate law just by writing the chemical reaction. You can't tell. You have to determine the rate law by performing experiments. And we say we can only determine the rate law experimentally. Okay? So, here's the rate. Oh, that's bothering me. Let me try that again. 2A plus 3B going to C. Okay? So, there's our reaction, and now I'm going to write the rate law. And initially, again, like we said, without performing experiments, we don't know the rate law, but we can draw or write what I can kind of call the skeleton rate law. The skeleton rate law. The skeleton rate law for this reaction is like this. The rate of the reaction equals, and I like to draw the concentrations of the reactants first because that's obvious, all right? The rate will always equal the concentrations of whatever the reactants. We know that because for this reaction to occur, A and B actually have to find each other. They have to find each other and collide. Therefore, if there's a lot of them, they can find each other more easily and the rate of the reaction will be faster. So we know that it is dependent on the presence of the A and B, and we know that concentration also influences that reaction rate. Okay, so this is the beginning of our skeleton rate law. And now I'm telling you, as a review as well, but there are coefficients associated with the concentrations of the reactants in this rate law. All right. Now, after we have that much done, and hopefully 90% of this is from intuition, right? We know that the concentrations of our reactants is going to govern the rate of the reaction. Okay? And so that much you should know. This much you might not know, but it's not terribly surprising. It's possible that the presence of one will influence the reaction faster because in some chemical reactions there are coefficients, so you know you need more of them, all right? But we do have to make sure we recognize that this X and this Y does not relate necessarily to this 2 and this 3, all right? So just because we see the 2 and 3 there doesn't mean that that is going to be 2 and 3, all right? So again, we're talking about the skeleton rate law initially. And one more thing that we're missing here is what's called a rate constant. Now, how are you going to remember that you need the rate constant? If you don't have a rate constant, your units will never work out, right? Because the units for this is molar. Units for B, concentration, again, molar. But rate is not ever going to be in molar, and it's never going to be in molar times molar, let alone if these are numbers here. Like if this is a 2, then that would make this molar times molar, which is molar squared, right? So rate is not going to be in molar or molars to the squared or third or anything like that. Rate is always in what units, Camille? Do you remember? What is rate always in?
Something over minutes.
Okay, it's molar over time. Time. And it doesn't need to be minutes. It doesn't need to be seconds. It doesn't need to be hours. But generally, usually your examples are written per second. But yeah, rate is always going to be in units of molar per time. And that will remind you then that you must need some sort of a rate constant that will allow the molarities here, that the product of all the molarities, to have at least a per seconds, let alone possibly more than that, right, in terms of units. Okay? So this is the true skeleton rate law, which I think is generally pretty straightforward and easy. You should be able to know what the skeleton rate law looks like, right, given the equation. So really all I'm doing is saying that the rate is equal to some constant times the concentration of the reactants. That's all. Oops, not the 3 there. And what we really want to take home to remember that concentration of reactants, no products, and that the 2 and the 3 do not relate necessarily to those values. Okay, now let's get back to this slide here. Here's some data. Can we determine what the rate law is from this data? All right, Sarah, could you help me out a little bit with this? Can you help me draw? So we just had this skeleton rate law from this reaction here. All right. Can you help me make the skeleton rate law for the data that's provided? Okay, Sarah, what should I write down here for my rate law for this data up here?
I am not sure.
Well, what's the first word?
Rate.
Rate. Very good. That's it.
Yes.
Rate will equal, now from this data, well, I mean, anything else that we know for sure regardless of this data? Sarah, what else might you know?
It looks like they give us a bunch of different rates.
They give us a bunch of different rates here. And then these, what is this A in this bracket, B in this bracket, and C in this bracket? What's all that mean?
That is the concentration of all of those.
That's right, the concentration of all of these. And because they're providing us concentrations of these things, these must be the reactants. The reactants. Does that help us? What else would we want to include in this rate law now?
So I guess concentration of A times concentration of B times concentration of C.
Very good. Anything else?
And then we know they're all raised to the power of something.
Okay, I'll use X, Y, and Z. Whoops. Didn't use it in order, but okay. What else? What's the other component?
And we need the constant.
That's right. A lowercase k, a rate constant. All right, so we have a skeleton rate law there. And now we need to, the first thing we want to do is try to figure out what this X, Y, and Z are. All right. Okay. Alyssa, do you happen to, by chance, remember what we did in last class to determine what the order of the reaction was with respect to A? And that's what we call it, right? The exponent up here on A, the exponent on B, and the exponent on C tells us what we call the order of the reaction with respect to that reactant, right? Remember what we did, Alyssa?
I think so. So we looked at like each individual reaction that they did with the different concentrations to find the XYZ. Like whenever we plug it in to find, like, with the rate that was provided and the two constants from that equation to figure out what, if it needed to be squared or tripled or
Okay. Very good. So if we wanted to determine the order of the reaction with respect to A, Alyssa, which two experiments do you think we should choose? Now, I don't have these experiments numbered, but this is 1, 2, 3, 4 experiments here, right? Which two do you think we should choose, Alyssa?
I feel like we should probably choose 1 and 2 because the concentration of A changes and the other two variables remain the same.
All right. Excellent. So what that does is essentially says we can take the rates for the first two experiments. The first rate is 0.002. The second rate is it's not 002, but 0002. The second rate is 0.0004. Again, molar per second here. So I know the rate for experiment 1 and experiment 2, right? I know the rate for experiment 1 and experiment 2. And I can compare how the concentration of A influences that rate. Okay? So I could write down that rate here for experiment 1, 0.0002, and I could write down the experimental rate here, 0.0004, 0.0004, right? And I can include, so I'm basically rewriting this rate law up here, which is a skeleton rate law, with some information from the experiments to see how the concentrations here influence the rate. Now, Alyssa said we chose experiment 1 and 2 because we were after the order with respect to A first. And so we chose experiment 1 and 2 because in experiment 1 and 2, only A was changed. So the contribution to the rate due to B and the contribution due to C will be the same. And so I really don't have to worry about their contributions when I'm just comparing this and I'm trying to identify the contribution of A. In fact, I don't even have to worry about my K, right? I can just say what the concentration of A is here compared to the concentration of A here. And what I see is concentration of A here in the first one is 0.01, and here it's raised to some exponent, and here it's 0.02 raised to some exponent. Now I basically have two experiments here, two equations, and it's always pretty straightforward. You can see what the x is simply by solving this, right? You don't have to do a lot of algebra. You can just kind of think in your head. All right. I can tell that, Taewon, what happened to the rate when I doubled my concentration here? What happened to the rate? What happened to the rate, Taewon? He's typing for us. The rate doubles. That's right. When the concentration doubles, the rate doubled. So, Camille, what does that tell us that x is probably equal to? 2?
Oh, wait, 1.
1, right. And that's a very good example. We have to be very careful because we think, oh, it doubled, it's 1. And that's why, in general, when I do these equations or do this sort of answer these problems, I try to simplify it for myself. I try to say, instead of using these values here, I use values like 1 and 2. Because essentially it's the same thing. So I can go like this. I can do this exact same thing, but I choose experiment 1 and 2 here. And this time I say the rate of experiment 1, we'll call it 1. And the rate of experiment 2, we'll call it 2. And then I can say the concentration of A, I'll call it 1. And the concentration of A in this experiment, I'll call it 2. And then I just have a really straightforward equation here, or two equations. And I can see very easily that these already equal each other. There was no contribution here, so it's 1. Now it's not 0. It's not 0, so don't think that, right? If I put a 0 up here, what happens, Camille, if I raise a value to 0? Do you remember that from math days? It turns into 1. That's right. So it's not 0. All right. So what have we learned from that business, Camille? What are we trying to figure out? What did we just learn?
I'm sorry, I'm confused by the question.
What did we just learn from all this stuff where we compared experiments 1 and 2? We wrote down all these equations. I explained how you can do it 2 different ways. What's that?
That the rate doubles.
The rate doubles, and
then it's raised to 1.
And that's right. And that the order of the reaction, of this reaction with respect to A, the order of the reaction with respect to A is 1. It's first order. And now we can write a new and improved rate law. The new and improved rate law looks like this. The rate equals, same thing, K, A, but now A, is we know, is raised to the 1. B, we still don't know what it's raised to. And C, we still don't know what it's raised to. All right, so we've improved our rate law slightly, but we still need these two orders. Okay? So we got just a small handful of people, but I'm going to break us into groups, and I want you guys to work on identifying what the orders for the reaction with respect to B and respect to C are. Okay? So I'm going to create the breakout rooms here and go. All right. So what did we learn? What did we learn? What was the rate with respect to B? Who was in there? Sarah? What was with the rate with respect to B?
The rate with respect to B was
1. Very good. And the way that we could tell that is we could tell that what experiments did you use to compare?
We used 1 and 3.
Experiments 1 and 3. Experiment 1 and experiment 3. Now, when I look at experiment 1 and 3, and I recognize that I'm interested in kind of looking at B, right? I don't double the rate or the concentration of B going from experiment 1 to experiment 3. I double it going from experiment 3 to experiment 1, right? And that doesn't matter how I write it down. But in my simple mind, to keep things as simple as possible, I'm going to put experiment 3 up here ahead, above experiment 1, just so my brain doesn't have to think any more than it needs to, right? And so I look at the rates, and again, to kind of simplify it in my brain, instead of writing, so this is, I have my skeleton rate law here, and I'm only going to be looking at B. A and C's concentration are the same in these experiments. So for rate, I'm just going to write, for the first one, 3, I say 1, and the second one, experiment 1, it's twice as much. So because it's twice as much, I'm just going to write 1 and 2. All right? And then the K stays the same, so I don't need to include it there, right? The concentration of C and the concentration of A stay the same. But the concentration of B here, it changes from experiment 3, it's 0.01, and experiment 1 is 0.02. So it doubles. So it goes from 1 to 2. And now again, what we're trying to find out is what Y is. And so that's how we could determine it was 1. All right. Alyssa, did you guys get to do C? Alyssa? Let's see. Who else was it? Camille.
I was in there.
Did you get to do C?
Well, we got it all written out.
Almost got it, huh?
Yes.
What do you?
I'm a little confused because the rate of change is the same, but the concentration is different. So I was thinking it was 2, but then I thought maybe it's like 1/2. I don't know.
Okay, well, let's look. So you said we're trying to again
Experiment 1 and 3. I mean 1 and 4. Sorry.
experiment 1 and experiment 4, like that. Now we're looking at C here, 1 and 4. That's nice because it doubles, going from 1 to 4. It doubles. So, whoops, I got to scoot this over. Rate equals, I don't have to write the K. Is that okay? Is everybody okay if I don't have the K?
That's fine.
And is it okay if I don't include A and B? I'm just going to say concentration of C, right? Raised to some exponent. Okay? So, and we said that the rate does what? What should I write down here, Camille, for experiment 1?
0.0002.
Okay. And 0.0004. Is that right?
No, it's 0.0002 again.
Oh, 1 to 4. Okay, good. Is it okay if I just write 1 and 1? Is that all right?
Yes,
Do you understand why I'm doing it that way?
because they're both 0.0002.
Yeah, the rate hasn't changed. And then I can just look at my concentration of C in experiment 1 and 4. What value should I write down here?
0.15 and 0.3.
But to simplify it for myself, what might I write?
1/2.
Or just 1 and 2?
2.
Does that make
Yeah.
sense? All right, very good. Now, what do you think?
Well, I originally thought double, but that doesn't really make sense.
So if you put a 2 here, 1 squared, that would work. But 2 squared should be what over here?
It's 4.
4. So that's not right.
Is
How-
it 1/2?
Is it 1/2? Well, here's the real thing. What number do we raise 2 to get it to be 1? Because there's only one number out there.
1.
2 to the 1, does that equal 1?
Oh, no, that equals. Yes. No,
No.
I don't know.
2 to the 1?
It's 0.
It's 0, isn't it? It's 0. Has to be 0. 2 to the 0 equals 1, and 1 to the 0 equals 1. Okay, very good. So we got our rate law now. The rate law for this experiment is, well, we almost got it. Rate equals, help me out here, Taewon. What do I have to write? Rate equals, tell me what to write here. K. Now you drew an uppercase K, but we know it's a lowercase k. Times, what's next, Taewon? Concentration of A raised to what value, Taewon? One. A to the 1. What's next? B to the 1 as well. And that would be it. I mean, I could put in here C to the 0 if I wanted to, but we know that C to the 0 means that C does not influence the rate of this reaction. Okay? So, we've made great progress. We're almost done. The only thing we're missing is what K is, because K is an actual number, but we need to know what it is. And with that number K, we also need to kind of identify what we call the, well, not what we call, the units for the K. So, why does it feel like I went from Camille to Taewon? I guess I was moving around because of the groups. But we'll go back to you, Camille. So, Camille, tell us, if you remember, what step do I need to do now to try to find out what that K is, what the actual value for that K is?
If I remember right, I feel like you have to plug in A to B, the concentrations of A and B.
That's right.
And then also plug in the rate and then kind of like do like that little like multiply divide thing.
That's right. And what experiment do I use? Any. That's right. It shouldn't matter. It shouldn't matter. As long as these experiments were all performed under the same conditions, pressure, temperature, mostly just temperature, then A, the concentration of A and B, it should have the same rate constant. All right? So we'll choose the first one. A's concentration, 0.1. B's concentration, 0.2. No, 0.0201. Okay? To the 1, K equals our rate, 0.0002. All right.
K would be 1.
Is it? Is that it?
Yeah, because it's the 0.01 times 0.02 is 0.0002.
You're right. Great. Okay, so our K is equal to 1 there. 1. So now our rate law is essentially done except for one tiny itsy bitsy thing. It's K where we have 1 concentration of A times the concentration of B. So there's our finished rate law, except for the only thing we're missing are the units. Sarah, do you have any idea what the units for this rate or this K might be?
Okay, so the rate is molar per second, so I think it's going to be, it's got to cancel those seconds out, so is it just seconds?
Well, you don't need to cancel it out. You need this side to look like this side, right?
Yes. So.
And what is A and B? What are A and B right now?
They're both molar.
That's right.
So you have molar squared. So it needs to be 1 over m times seconds.
Very good. And here it is again. Beautiful opportunity. Can't pass it up. Where do you go to, what do you do to get rid of molars?
You gotta go to the dentist.
Wonderful. Wonderful. Very good. Got to go to the dentist. Okay, so there is our review on how to find the rate law from initially starting with, we started with skeleton rate law, right? Skeleton rate law. And then gradually work our way up to, whoops, that wasn't the actual skeleton rate law for that problem, huh? This is our skeleton rate law, right? Skeleton rate law, and then we work our way up to the rate law without the K, and then we solve for the K. Okay, very good. Nice review.